generally, before I will start my presentation, I would like to acknowledge my co-authors, and this is the result of collaboration between my group, Mechanics of Advanced Materials at Loughborough University, and Huazhong University of Science and Technology in Wuhan. You can see that people are there. So this is a general idea about the type of the paper that I'm going to present, and we'll start with the motivation. So just now, in just contrast to the previous presentation, this is a material much softer and used for totally different kind of the application. And the idea behind it is that there is nowadays a significant need for materials which can be used in regenerative medicine to produce artificial tissues or substitutes or soft implants, if you want, compared to the one that you have been shown in the previous presentation. And the problem with these materials is that they are less studied, they are less traditional than our standard conventional structural materials. When you deal with the ideas of the application in biomedical structures and tissues, then what you would need is good biocompatibility. You need to have a structure which resembles the structure of the tissue that you are substituting, so that the cells would be happy to live in the new artificial house for them. And then we also need to do, and this is a significant challenge nowadays, understand the mechanical part of this behavior. Obviously, doctors and biomedical scientists, they have covered the two major parts of this, but also these materials, they need to perform some load-bearing functions or structural functions, and so that's why the mechanical properties should be properly understood. And this is the motivation behind the study. And now, so just I will give you an idea about the materials. So just my bet is that not many people just have seen this type of the material. This is bacterial cellulose hydrogel, and this is what you can see. And for you to get an idea, this is a composite material with a very special type of the matrix. The matrix is water. 98% of this material is water, and all the other parts, 2%, it is the nanofiber network which holds this water together. So, but when you have this like this, it seems like a polymer material, quite a soft one. You go, so just do SAM, and you will see that in plain, because this is a bacterial cellulose, so just the reason is that it is produced by bacteria. So obviously then bacteria is being removed, so just you don't be afraid, but generally this has by default biocompatibility because it is biomaterial produced in a natural way. So if you look, so just it is produced in a petri dish or so just whatever you are doing. So when you are looking from the top, you will see this type of the network. So just this probably you wouldn't see here the length scale, but the diameter of the fiber is around 20 nanometers. So when you are looking from the side, you will see the structure. This is the layer what you can see from the top. From the side you can see that there is, and here is the notion of the directions that we are using, that in the out of plane direction there are some nanofibers which are linking this multi-layered structure together. And this defines a very interesting type of the material's behavior and performance. I would more concentrate on the deformation. Fracture will be given at the end, don't worry. But so just we must understand the material before we can start speaking about its more advanced properties. So first of all, there are different ways how to deal with this material. Many people are doing with the dried material. Then they prepare the specimens, use them into the system, and test the properties. But then they're removing a component which mechanically you can consider that it is not load-bearing because we have only significant bulk modules and no shear modules of the water. But it is very principal, and don't forget that we are consist of a large amount of the water, and we are still so just having our shape more or less, which changes with time. So we have used another type of the test, which is called in aqua. So all the tests were performed in the water at the temperature of the body. So that's why we are presenting the behavior of this material as close to this natural environment as possible. So, and here up, so just, yeah, you can see here, this is the specimen, which is in the grips, and these are just, yeah, so just spheroids. These are nothing else as the bubbles in the water. We can't remove them, obviously. So you should concentrate only here. And what you can see, there is a significant level of extension, and then materials start localizing its deformation, thinning, and then finally there is onset of the crack and its propagation. So this material, it is just, and we have also another part of the development. We are working with the Non-Women's Institute in Raleigh. So this is a discontinuous material. Its behavior is not properly reduced to the behavior of continuum. The reason for this is that your fibers, if it were, say, CFRP, then any movements of the fibers, they were constrained by the matrix, which can be brittle as epoxy. Here it is the water. It gives some resistance but not strong. So that's why most of the deformation is through the reorientation of the fibers in the water. That's why generally when you are loading it, stretching it as was shown here, then first of all the segments between the intersections, they reorient themselves in the direction of the stretching. And because of this, if you will start looking, we will have this non-linear type of behavior, and we have generally, if you look depending on the amount of stretching, we have, depending on the microstructure, and it is becoming more and more stretch, as you can see here, different types of the instantaneous Young's modulus. You can see here it's constant, then linear increasing, then constant at the higher level, and then it is decreasing, and then it is zero when it is failed. So then, and it's another part to understand, coming back to this slide, that unfortunately we cannot perform our test in the intention in out of plane direction because the specimen is very thin. So that's why we have a combination. We can stretch it in the plane, but in out of plane direction we compress. So that's why, so just you can see here the results for the compression. So just compression is clearly that it starts at the very low level because it's only a few fibers which are taking the load, but then when it is nearly fully compacted, there is the response of the entire so just material as it is. And we have 3 stages here as well. Another interesting point to understand here is that, like in typical microstructures, also just in contrast to the continuum, what you can see here, we have a zero Poisson's effect. You can see that at the same scale, this is the specimen compression, and practically here it shows to you, so just schematically, that generally its diameter doesn't change. It's clearly because when you're compressing, so there is no lateral extension because simply the water is flowing out, and then it is being compacted on itself. So, good. Then it was so just, it was easy, more or less, when we were speaking about the linear loading. Now we are going to cyclic, also just loading, unloading with different amplitudes. And we can see here, so just a very complex type of behavior. You can have different types of the loops. So just you can have the curve, which is obviously, it's a master curve, and you can have the changes in different parameters with the type loading, unloading. So just it's also just, this part is properly so just published, and you can look if you are so just. But what we immediately can understand that there is a significant component which is plastic, which is also should be accounted for. Now, so it's not the end of the story, because so just you've seen this material, it's polymer, then probably it behaves also so just viscously. So it is indeed. So that's why we've done in-plane tensile creep. We can do tension, but we have done the out-of-plane compressive relaxation. And you can see here the typical type, so just of creep or relaxation curve. Significant drop in the very, so just very quickly, which demonstrates you low relaxation times of this material. And so also, so just to throw another level of complexity, if you will look at the strain rate sensitivity, many materials, they demonstrate one, so just where you do have this with the constant parameter. What we can see here, it is the change from the insensitive to strain rate hardening, then softening, then insensitive. All the strain rate sensitivity parameter is going depending on the strain rate from positive through 0 to negative and then coming back. So this will give you the idea about a very complex type of the material behavior. So, and why I'm describing is that it is deformation. In order to go to the fracture, obviously all the elements, elasticity, plasticity, and viscosity should play a significant part, and the same is needed for us to produce the models of this material. So now go and I will skip this, but this is about deformation mechanisms, how they will go, but I'm aware that the chair will probably push me out of this place pretty soon. So let us go to the fracture, and these are the tests in the fracture. So these are the specimens. The red part, we will put the pattern simply to look at how this process evolves, and we were considering 4 different types of the specimens, all having undamaged ligament thickness of 4 millimeters. So we can have 4 millimeters without a notch, or we can have 6 millimeters with single notch of 2 millimeters, or we have 8 millimeters with 2 notches, 2 millimeters each, or one with the center notch of 4 millimeters. As you can see, we are trying to compare the behavior of the material which notionally only 4 millimeters broad in its narrow space of the specimen. And you can see here evolution of the specific specimens in time. And here are the results which I wanted to demonstrate you. So in the red curve, the lowest one in many cases, as you can see, it is the material without a notch. So you can see here that generally introduction of notches makes the material tougher and stiffer. So the reason for this is, and we observe this in another non-woven materials, is that your crack, which you have introduced in the system, in continuum it will result in different types of the singularity. So just pretty straightforward in elastic case, a little bit more trickier in the elastoplastic or viscoelastoplastic case. Here, what we have the situation, you can't even at this resolution of several microns resolve single fibers. The crack, effectively, it crosses through the nanofibers, but the fibers which are at the very notch, they are not affected by this. So there's obviously a local local distribution, but in reality, because they have a possibility to avoid the crack propagation by simply reorienting and transferring the load to its neighbors, and result we have a stiffer situation. So, and very quickly, in order to model this material, you can do this continuum approximation. You need to introduce the discontinuous approach. We have done this, and we have obtained some of the parameters. And here is simply, I'm aware that I must finish. The idea, this is just to give you a flavor how complex can be materials, how tricky they are in their behavior. An interesting point to remember is that materials with the fibrous networks without a matrix, they are demonstrated negative fracture toughness. If you want, they're becoming stiffer when you introduce the notches. And that is it. Thank you very much.